Great. Okay, so as I said yesterday, we talked about the interrupting rating for overcome detection device. Today we're going to talk about the withstand rating of equipment as well as the short circuit calculation. These are engineering topics, as I mentioned. Take a 1000 amp switch gear. Now you guys have a 1000 amp switch gear, right? Inside this switch gear, you're going to have three short circuit rating. Number one is interrupting rating. I'm going to put this one, number one, with blue. Right here for the circuit breaker, interrupting rating for short circuit. Let's call it short circuit interrupting rating. So we can, it's applied to short circuit interrupting rating. Or, so short circuit interrupting rating. This one I'm going to put it at 85,000 amp. So this is a 1000 amp circuit breaker that interrupt up to and including 85,000 amp, right? That's how much this big boy can handle. Any question, guys, about the interrupting rating? So this means this circuit breaker will be safely able to open up to an 85,000 amp short circuit, be it ground fault, be it single phase to phase, or be it three-phase circuit. So that's the first short circuit. The second value, guys, withstand rating. The withstand rating, the switch gear has something called short circuit withstand rating. Withstand rating. The withstand rating is how much the copper inside the panel can handle the mechanical stress because of the short circuit and the heat. Does that make sense? How much this panel can handle, withstand heat and magnetic force created by the short circuit. So that's called withstand rating. Usually it's the same way, 85,000 amp. So this switch gear can handle a withstand rating up to 85,000, meaning it can handle up to 85,000. It's intact. You go higher than that, the switch gears itself is going to blow. If you go higher than that, the circuit breaker might actually, the contact of the circuit breaker might weld together. They don't open, they weld. Okay, any question, guys, about the interrupting rating? Interrupting is rating of interrupting the current. Withstand is rating of being able to handle the stress for the buses, right? Stress is imposed on you. You're going to be able to handle this stress for 85,000. Okay, so that's what we're going to be talking about. The last one, guys, is the short circuit. The last one is the short circuit. Right here, the short circuit, if I short right inside this panel, that's called available short circuit. Available short circuit, that's if I take phase A, phase B, and phase C and bolt them together. Can you imagine that? Bolt phase A, phase B, phase C together and flip the switch on. I'm going to throw this value for you. I'm going to get 81.35 thousand amp. That's called the available short circuit. The available short circuit. Any question, guys, about these three things? The chapter that we took yesterday, overcome detection device, talked about the interrupting rating of circuit breakers. Today, we're going to talk about the short circuit rating for equipment, how to calculate the short circuit. How do I come up with 81? Why not 83? Why not 84? How do I come up with the 81.35? And also, how do you come up with the withstand rating of the equipment? Withstand rating of equipment, guys, they do UL will take the switch gear and literally, physically, mechanically pump 85,000 amp in the switch gear and watch what's going to happen to it. If it's still there for a certain amount of time, of course, not forever, for say 3 cycles, if it's 3 cycle rated equipment, most of them for 3 cycles, they should be able, 3 cycles, 3/60, 1/20th of a second. For 1/20th of the second, that switch gear should be intact. If it's NSA switch gear, you're talking about 30 cycles, half a second. For half a second, this switch gear should be intact when you pump that amount of current inside it. Any question, guys, about these 3 values? So yesterday we talked about the blue value, the interrupting rating for equipment. Today we'll talk about the withstand rating. Most of the time, the withstand rating is equivalent to the interrupting rating of the equipment. That makes sense, right? because you want to interrupt higher than what the equipment can handle, right? If my equipment can handle for 85, why should I limit my interruption to 65, for example? So usually the green and the blue values most of the time are the same unless you have current limiting fuses. If you have current limiting fuses or circuit breaker, then this could be 85 and this could be, the withstand rating of this could be 70. Why? Well, in this case it can't be 70 because of the short circuit. This could be 83 because the short circuit is 81. The relationship between these two guys, the values, is usually the 85 kiloamp must be more or equal to the 85 kiloamp, and the last one, the red, and the red also must be, this must be more or equal to the 81.35. Make sense? This value must be more or equal to this value, and this value must be more or equal to this value. Or equal, remember the equal. Any question about these three values? Interrupting rating for circuit breaker, withstand for the panel, and short circuit. If you grab the three phases together, bolt them together, and flip the switch. Okay, so what we're going to do today, guys, we're going to talk about the short circuit calculation. Short circuit calculation, I'm going to show you, we're going to be using power tools for window next quarter, and we will do the calculation step by step. We're going to do short circuit calculation for three-phase, mostly three-phase. Okay, a couple of things, guys, when we talk about short circuit calculation that you will be able to do. We call it the point-to-point method. This is not lighting point-to-point method. Remember the point-to-point method lighting? This is short circuit calculation point-to-point. And the whole idea of short circuit calculation, Ashley, is to come up with this value. How am I going to come up with this value? That's what you're looking for. How am I going to come up with this value? Because based on this value, the 81.35, I can size, right? I can size the withstand for my equipment and the interrupting for my circuit breakers. So you always start with the available short circuit. How am I going to calculate the available short circuit? Can you guys with me? Yep, Chad. We're gonna, because the available short circuit is the start point, your start point. So moving on. So we're gonna do a short circuit calculation using the point-to-point method, and then we're gonna look at tables. You guys are gonna, for this one, we're gonna be using later on power tools for window, SKM. We're gonna be using it next quarter, a software called Power Tools for Window. Beautiful, easy. Today we're going to do it by hand, though. Very simple one by hand. Show you how to do it by hand. I don't want you to do it by hand because there's a lot of softwares that can do it faster, easier, better, more accurate than we're doing it by hand. But just to give you a flavor of that. To do it by hand, we have some tables and charts we're going to be looking at today. And then based on this, we do the coordination, guys, selective and non-selective system. By now, you know what a selective system. A fully selective system, guys, if I have a short circuit in this brand circuit right above your head, I want this circuit breaker to trip. Oops. I want this circuit breaker to trip, not the circuit breaker that feeds this pan, right? We'll talk about the selective coordination, and to do the selective coordination, we have to do time current curves. We looked at these yesterday. The higher the current, the faster the system will trip. The higher the current, the faster the system will trip. So these are a few things, guys, that we need to know. This is just a disclaimer. When you do the tables, there's a lot of, the answers might not be the same because of approximation. We don't use the tables. We usually use softwares, and from the software later on, guys, you're going to see. Remember how estimating software you guys are using? The power system analysis software has a library that comes with it. If you need a transformer, all the transformers that God created are in the library. Conductors, all the THHN, THHW, XTHHN, XTHHW, all these medium voltage, all these cables, guys, are put as a library. They are in the library of these systems, so you can pull all this information, the impedance and so forth. Okay. Okay. When they do this, the start point, guys, for all the calculation is the transformer. The start point is always the source of the power, the transformer. I'll show you in a second. So for the transformer, suppose I have a 25 kVA transformer, you are allowed you 10% plus or minus impedance, So you're going to see, always we start with the source, the transformer. You're going to see in a second here. Okay, arrive reasonable. This is all soft. Here's the key point. I'm not going to, the key point is right here. We always use software programs, PTW, more accurate. But your start point is going to be always the transformer. Transformers determine the short circuit current at various distances. So step number one, and I'm going to go all the way to the examples because it makes a lot of sense to do it. Okay, short circuit, 7 steps, and a couple of things about, let me go directly into the calculation, guys, before we go into that one, and just show you the whole calculation business that they do. So let me, give me 1 second here to plug in and go into, go into the whole calculation. I think I do have a 18. Okay, I think I do have a picture of the whole calculation. There you go. Okay, so here's your load calculation. Very simple, very easy. If you guys look at this one and you follow up with me, you would never do it by hand, by the way. Never do it by hand. To do this, can you guys do me a favor and go to page, this one, this particular one is in page 427, page 427. Okay, this is how we do a short circuit calculation by hand. Thanks God we don't do it by hand all often. Here's how we do it by hand. First of all, the start point, if you guys follow with me, you would never again forget it again. This is a single phase transformer, single phase. The most important thing, I have a couple of points I need to do the calculation on. Here is point A. Can you guys see? First of all, we need to find at point A. Can you guys see where point A is? Right here. And I need to do it. Here's point A. So let's go right. We always start by the transformer, right at the terminal of the transformer. Right at the terminal of the transformer, guys, here's the information about the transformer that I have. I have 167 kVA transformer, 12240 volts, single phase, 2% impedance, and full load current of 696 amp. Full load current of 696 amps. Okay? Any question about what we have? The first thing you usually do is we find the full load current, which is I, full load current, equal the 167K divided by 240, and this will give me, should give you 696 amps, right? Should give me 696 amps. Can anybody try it? Can anybody try that one? 600. If you take 167 divided by 240, you should come up with 695.8, which is 696. Any question about step number one? That's the first thing you do. You start with the transformer. Find the full load current of the transformer. Any question about this, guys? If that was a three-phase, what would you add next to the 240 if it was three-phase? 1.73. Okay? Step number one. So step number one, guys, we're going to find the full load current. Here's step number one. Done. After step number one, any question about step number one, finding a full load current of a transformer, single phase, you use single phase formula. Three phase, you use three phase formula. Okay. Based on this information, the second step, step number two, is finding the short circuit right now here. I want to find the short circuit right at point A, which is at the terminal of the transformer. Here's my transformer, guys. I want to take the two hots and tie them together right at the terminal transformer and turn and flip the switch on. That's the worst scenario that you could ever happen to you, right? If you do that, then here's how you find the short circuit. There's a multiplier called M1. You take 100. Can you guys see the impedance here? Everybody can see 2 is the impedance, the 2% impedance. They multiply it by 0.9 always because they assume that it's plus or minus 10%. So if something is a plus or minus 10%, always minus 10% is the worst. The low impedance is the worst because it gives you more current. Okay? So this is how they came up with a multiplier of 55.56. Okay? And then you multiply this multiplier by the full load current and the available short circuit right at this terminal. if I go short these together, here's the available short circuit. Any question? Right at the terminal of the transformer. Piece of cake. We've done it before, guys. You take the full load current and divide it by the impedance. This is what they did. They took the full load current with this M1, they call it M1. This is exactly the same as taking the full load current and dividing it by the impedance. The only thing they added is they added 10% reduction in the impedance. And that's why they multiplied by 0.9. Okay, so your impedance will actually be 0.9 of what's listed for, because it could be plus or minus. Any question, guys, about finding the short circuit at the terminal of this single phase transformer? Up to this point, you guys have done it. We've done it before. We took the full load current divided by the impedance. That's exactly what they did. The only new stuff here, the only new stuff is really that they multiplied it by 0.9, because the impedance here, that impedance right here, is plus or minus 10%. So if it's plus or minus 10%, the worst scenario is minus. So if I were to make this one 10% minus, how do you make a number 10% minus? You take a 0.9 and multiply it by 2. Here's the new impedance, and that's basically what they did here. Any question, guys, about finding the short circuit at the terminal of the transformer? Okay, now look what they're going to do. We're going to do downstream. This is where, up to this point, you guys have done it. I know we've done it. Downstream is the new stuff. Downstream, which is now I'm going to go to red here. Let's say red. I need at point CC, right in here. Can you guys? I'm going to go short at point C, line to line. And this point, can you guys see that this is 25 feet away from the transformer? And we're using two conductors, number 500 kcm each. Two conductors, number 500 kcm each. So I found the short circuit at the terminal of the transformer, Alaripo, right here. I shorted them, right? It's hard to do. There's the short circuit right at the transformer. Now I move 25 feet, and I need to find the short circuit because there's another panel. Cool? Why do I want to do it 25 feet? Because I put another panel there. This is at the main panel. It's 38,000. Sub panel downstream, I need to find it. When you go downstream, guys, the conductors act as an impedance to choke the current. Okay, so the new stuff that you need to know is there's a new formula. This formula is called F. So for this single phase, it's the F is equal to times L, the length, I is the current, we found it, divide N by the number of conductors in parallel, C is the factor for the conductor, we're going to find C, and ELL is the voltage line to line. So so this is a formula. If you are to do it, bring the formula with you. Cool? The F factor, they call it, the F factor. Okay, where does the 2 come from? The 2 is in the formula. What is the L? 25 feet. Can you guys see 25 feet from here to here? Everybody can see that L is 25 feet? Can I have thumbs up? L, 25 feet. Tell my friend. L is 25 feet from here to this panel. Make sense? No? I, where's the I? I is the short circuit right at the terminal of the transformer. Everybody can see that I is the short circuit right at the terminal of the transformer. Okay? N is the number of conductors in parallel. How many conductors do I have in parallel? How many conductors do I have in parallel, guys? 2 conductors. 2 conductors. C is the factor. We're going to find this C in a second. And ELL is the voltage line to line. So up to this point, everything you guys should be able to find. Here's a voltage. Here's in parallel. Here's the distance. Here's the short circuit. This is coming from here. 2 is in the formula. The only thing I want to go is this C factor, 22185. 22185. Do me a favor, guys. If you can go to page 426, please. 426. 426. These feeders are conductors per phase and 2 steel conduits. They are in 2 steel conduits. Are you guys going to page 426? No? Okay. 426. Page 426. Good. Okay. So if you guys go to this page, this will give you the C factor for conductors. They call it the C factor. That takes the impedance into consideration of the conductors. The first thing you need to decide in this table, guys, is it copper conductor? Yes. The bottom of the table is actually for aluminum. One for copper, one for aluminum. The last one is for busways. Cool? All right, let's look at the upper one because it's copper. If it's copper, you need to decide, is it 600 volt or higher than 600 volt? It's 600 volt system, right? Less than 600 volt system, 240. And is it non-magnetic or steel conduit? Am I putting them in a steel conduit? Can you guys see where it says steel conduit here? Steel conduit. So do me a favor. What size conductor? 500. Can you go all the way to 500 under 600 volt steel? What's the number? 600 volt, 500 kcm steel conduit. What is the C for this table? 22185. Can you guys see where this 22185 came to be? 22185. Now what the heck is this? The question is, what the heck is this? This is the impedance. This is equivalent to the impedance of the conductor. This is equivalent to the impedance of the conductor. Now, thanks God, on the softwares, we don't have to mess around with tables like this. All of them are embedded in the system. That's the impedance, the R and the XL and the XC of your conductor, the impedance, the Z, equivalent to the Z of your conductor. Okay? Can you guys see that they can give it to you at different conductors for copper and different voltages? Cool? Okay, everybody knows what the 21.185 came to be. How about the 240, the voltage? When you do that, you end up with a factor, F factor 0.18. Then you use this formula to convert it into the M2 factor. They call it the M2 factor. 1 over 1 plus F, just plugging it, equal 0.85. Then you multiply this number here, can you guys see that, by the new factor, 0.85. Can you guys see now I end up with, right at this point, 32.887 short circuit. Now, can I get you guys to understand that the highest short circuit is going to be at the terminal of the transformer? The further away I go from the transformer, the less the short circuit would be, right? Can you guys see that it was 38.6? When I went 25 feet down, it dropped down to 32. Okay, let's go to one more point. Here's one more point. Let's use for this point blue. For this point, I want to have a point E. Can you guys see where point E is? Right here. I want to go short circuit at point E. Point E is 25 feet away from point C. Same thing. Here's my point E. I need 2 times L times I divided by N times C E. 2 is constant. 20 is the feet. 32.867. This is the short circuit. Can you guys see it? Plug it in right at this point. And divide by the voltage. Okay, now let's see, guys. I have 2 AWG cover conductor in steel. Can you find me the C factor for number 2 steel from this table that we're looking at? Number 2 steel. What's the factor for steel? Number 2 conductor under 600 volt.
5,906.
Thank you. 5906. That's the C factor for this conductor. Can you guys see where the conductor is? Right here. Number 2. How many of these conductors, Nick? 1. So that's where the 1 here coming to be. Can you guys see that 1? Okay, so it will knock it down to 93%. It knocks it down. So you grab it and put it back, and into this factor it becomes whatever short circuit here, it's going to be cut by almost half. So then you multiply the available short circuit by 0.52. It will give you, right at this point, we went down to 17,000. Okay, here's my point for you. Look at this, guys. Look at this number here, this number here, and this number here. What's happening to the short circuit as I move away from the transformer? What's happening to the short circuit as I move away from the transformer? It's going down. As I move away from the transformer, the short circuit is going down. That's it. Any question? Any question about that? What you see on this side is for the ground, line to ground. This is line to line. Line to line when you take hot with hot and you tie them together. A ground fault, so we took a calculation at point C and at point E. At these 3 points, A, C, and E, calculation. On this side, we did the same calculation for line to ground. Can you guys see line to ground? Because you can have, on a single phase system or 3-phase system, guys, you can have line to line, here's line to line, or you can have line to ground. The line to ground will be different value than line to line. Okay, if it's line to neutral or line to ground, can you guys see that? The same thing, you take the same amp, divided by the same multiplier, get you the same multiplier, exactly like the 3-phase. Can you guys see that? Then you have to multiply by the formula. This is by this number. They want you to use this number, 1.5. I put question mark on this. They want you to increase it 50%. Because a ground fault could be under certain circumstances higher than a short circuit. Highly unlikely. So you end up with a 58. Then you plug it into this formula. The same thing, 2L, I, and C, E line to neutral. The only difference is we're using line to neutral voltage here, and we're using different voltage. The same conductor. Here's my multiplier. Then at point D, I have 37. You go down to point F, same thing. You plug in your numbers, and at point F, I have 12. The same thing, guys, you can see the ground fault is going what? Going down. The ground fault is going down as you move away from the transformer. Yes, sir. Rule of thumb. I would put question mark next to it, though. If it's on a test, yes. I'm going to be testing you guys on that one when we have power tools for window. Power tools use it different. Yes, sir.
Just a question about the cable.
Yep.
Under the 600 volts, so that's 600 volts and less.
Yes.
And then it would be 5,000 volts or less.
Yes.
Okay.
Absolutely. Yeah, higher than 600 volt. Higher than 600 volt. That 5,000 would be higher than 600 volt up to 5,000 volt. If that makes sense. And that's the insulation of the conductors, Nick. The conductors come in these insulation, either 600 voltage insulation or 5K, 15K, or higher than that. These are the insulation rating of the conductors. Any question, guys, about this? Any question? So that's basically what a short circuit is. Really what I want you to do, Rob, is understand one little thing. The more you move away from the transformer, the lower the short circuit would be. That concept is unreal. This is the opposite of the voltage drop. The voltage drop, guys, the more we move away from a transformer, the higher the voltage drop. So these are two very important factors that going opposite each other. I want the equipment to be far away from the transformer, so the short circuit will be low, so my equipment will be cheap. Great idea, Chad. Oops, wait a minute. If you move your equipment away from the transformer, what happens to the voltage drop? Goes up. So you're going to find that happy medium between the equipment being far away and the voltage drop issue, as well as close enough and the short circuit issue. I always tell when I do the training, I say, the only advantage of having equipment far away from the surface is the short circuit will be lower. Lower means better. Short circuit lower means less damage, less arc flash, arc fault, arc blast. So it's safer equipment. Less PPE that you dress up, yep. Not less protection, less protection gear that you need to dress up when you work on energized equipment.
So, but will it lessen the material?
Cheaper equipment.
Cheaper equipment.
Cheaper equipment, yep, yes, sir.
But would you lose that cost by running higher gauge wire?
Then you have to have the happy medium. I'm not saying that this is a guarantee that move your equipment away from the source. Yeah. The panel next to here's what you need to understand. We don't throw the panels, guys, based on the short circuit. We put the panel where we need to, and then we design the short circuit to match. But you have to understand when you do short circuit calculation, the panel close to the service transformer will have a very high short circuit compared to the panel that's further down the system. Any question guys about this calculation? So that's without getting into the itty bitty area. That's basically how you do it for single phase. So let me see if I can have a couple of things. So we, okay. All right. So let's go here. This is the riser, guys, for the system that we have in our building. Can you guys see it? Look at this. Right at the transformer, the terminal of the transformer, I have 37, almost 35 kiloamp. If I go downstream, it knocks it down to almost 31 kiloamp just by the impedance of the conductor, So if I ask you, Nick, my friend, and I say, can you go please do me a favor and do the calculation right in this? Would you guys expect the short circuit right here to be higher than 31 or lower? If you say, if you write in your resume that you know how to do short circuit calculation, and you come interview with me, and I ask you this question, I said, at the service you have a short circuit 31,000, and I moved say 100 feet to downstream panel, right? You see downstream. Would that short circuit be higher than 31 or lower? Be lower. The impedance, it chokes the current. So this value here could be not down based, I'm just going to throw this, it could be as low as 22 kiloamp. What does that mean to you? Means the equipment downstream could be rated for lower value. Cheaper equipment. Okay? Any question guys about this? How did they calculate the value right at the, always start with the transformer. You always start with the transformer. This is your start point. So when we do short circuit calculation, guys, here's how many calculations you're going to have. You're going to have one calculation here. You're going to have one calculation in this switch gear, 2. You're going to have one calculation for every panel. 2, 3, 4, 5, 6, 7. I have 8 here, 8 calculation. Usually these we stick 8 calculations. I have to have 8 calculations, meaning I need to short circuit for 8 panels. And based on these 8 panels, 8 calculations, I can size each panel. So this panel could be rated right here. The insurance could be 22 kiloamp, withstand and interrupting. This, this is a gutter here, but let's just say this, because it's closer, or this is because it's bigger, could be rated for 35 kiloamp. Could be rated for 35 kiloamp, based on the available short circuit on it. When you guys use the software, one second, I'll let you go. When you use the software, we're going to build a riser in the PTW software that we have, exactly like you do in Revit, and we're going to run the analysis on it. And the software will assign a value right next to every panel in your building. We only care about panels. Loads downstream, not a big deal. Only panels, distribution systems. I can do the calculation and find right at this elevator equipment the short circuit here if I need to. Elevator control panel, I can do it. Most of the time we stop down to the panels, guys. Usually 100 amp panels or higher, that's we do the calculation on. Any question about that?
No, my question is on the 9 intra side.
Yep.
The short circuit counts for transformer. Why do we multiply it by 1.5?
They assume that the ground fault at certain values with certain impedances could be higher than the short circuit, higher than the face-to-face.
So would you take it as kind of
Rule of thumb as of now. Yeah. Most of engineers, guys, take the ground fault equal. The worst scenario when we design, the worst scenario, these numbers that I'm throwing these are 3-phase short circuit values. We use the 3-phase short circuit values. The ground fault, we assume the ground fault is not going to be higher than the 3-phase. The 3-phase is the worst scenario, and we move from there for 3-phase systems. Okay, so that's basically what calculation is. Let me throw a couple of I want to prep you guys for what's going to happen next quarter. Then we get into the overcurrent protection coordination. I'm sorry, Rob, do you have any question?
More of a light question. I was looking at that last picture, kind of interpret that as like a bus bar.
Yeah, this one here is actually a terminal block, terminal box. These are what they brought the feeder and they tabbed the feeder. Can you see how they're bringing it here?
It's the same principle as a bus bar.
It's really no, the bus bar is manufactured. It has a terminal in it, and you're just tabbing into it.
Well,
It's a gutter. Imagine a gutter with lugs inside it.
but if your distance to the gutter becomes length, do you calculate that?
Yes, yes, because it's gonna take every time you have length, you have impedance. Good point.
That is suitable for like bus bars then? It's not as
Yes.
simple.
Yes, it's right here under. If you can you see where the bottom of this table, the last one at the bottom? It's actually for bus bars. Yep. The softwares, Rob, when we do softwares, the software will ask you what type of wires are you using. If you're using wires and conduit, you can pick PVC, EMT, rigid, and THHN, THHW, TW, all the insulation. Okay, over the second thing, guys, of this is overcompression coordination. If you have overcompression coordination, here's what I'm going to show you a curve for. Here's a two circuit breakers. If you have a two circuit breakers, here's one circuit breaker, and the other one is another circuit breaker that sits something like this. This is the time, and this is the current I. And as I said yesterday, right in this zone here, this is fully coordinated except where? Except right in this zone. Can you guys see that this zone here is miscoordination? If these two, so let's just say this was a 20 amp and this was 100 amp. So this will be 100 amp. This will be a 20 amp. Cool? So can you guys see that they're not, if they're coordinated, they're not touching each other. Are they touching each other anywhere else except at the bottom? Okay, suppose that we have, let's just say, take an example here. We have a short circuit right here, and this short circuit was 4,000 amp. At 4,000 amp, let's say we're going to trip in half a second, 0.5 of a second. So can you guys see, because they are touching each other, both of them will trip. Both of them will trip at this value. Let's take another example. Let's take, I have a short circuit here, let's say 3,000 amp, right here. Can you guys see 3,000 amp? It will trip only, let's just say at 0.4 second. Which one of them is going to trip right here? Did that point, when it went up, did it touch the green? Ask yourself, did it touch the green? No. So would the green trip then? No, it wouldn't trip. So that's what they call it, over current protection coordination. So I am fully coordinated in this area. In this area, guys, up to this area here. Oh, I'm going to use that color right here. This area is fully coordinated. Anywhere in this area. Can you guys see that? Anywhere in this area is fully coordinated. Whatever happens here, it's going to coordinate. But where I don't coordinate is right in this area, that green, the blue. So if there's a short circuit, very high short circuit, both of them will trip. I'm going to leave it at this because we're going to come to, you guys are going to do an overcompression coordination with Chad next quarter. So you're going to learn about this. The more you learn now, the easier it would be when we move into the overcompression coordination. What a coordination means, the overcompression device closer to the system will open, guys. Here's a fully coordinated system. Look at this fully coordinated system here. I want to draw how this would look like with fuses. Take this. Here's fuse number 1. Looks something like this. And here's a fuse number 2. It looks something like this, right? So let's just say this is a 200 amp fuse, and this was a 50 amp fuse. Here's a 200 amp. This is a 50 amp. This is the time. This is the current. Are they touching each other? Is this fully coordinated? The question is, when you look at it, guys, if it says fully coordinated, are they touching each other? Are they overlapping? No, then it's fully coordinated. That's it. If they touch each other at the bottom or anywhere, then they're not coordinated, fully coordinated. They are coordinated, but not fully. Not fully coordinated. What does that mean? Meaning, suppose that this short circuit right at this point here, guys, if this goes, say, 11,000 amp, at 11,000 amp, the big boy will trip. So this means the short circuit here is actually, say, 10,000 amp. 10,000 amp. Oops, 10,000 10,000 amp. So up to 10,000 amp, this guy is taking care of it, and we are guaranteed that this will never go higher than 10,000 amp. So if it goes higher than 10,000 amp, then we're in this area, a short circuit right in this area, right? And you need which one to trap? The main to trap. Any question, guys, about fully coordinated system? What you are looking at a fully coordinated fuses, fully coordinated fuses. Please remember the graphics, because that's what PTW later on is going to be talking about, fully coordinated system. This talks about the time, guys, they coordinate, and I'm not going to get you into the timing and all this good stuff. It's all about timing, guys. If you look at this here, we got it. If I want to make things coordinate or not coordinate, I can shift things around, make it slow down to get my coordination. Okay, so we can 25. I have a couple of. Here's the table that we have in the front of you, and do me a favor before we move into this one, guys. I would like you to look. Here's the table that we have. Everybody knows how to use kind of this table. If you can see, this is the steel, non-magnetic, and for copper conductors, 3 conductors in a cable. This is conduits. The bottom one is aluminum, and the last one is busway. This is the multiplier F and M2 conversion for F and M2. This one is fully selected coordination. Take this. If you have a fuses, if you want fuses, guys, to coordinate fully with each other, here's the rule for fuses most of the time. Most of the time. So Rob, if I want to guarantee coordination between 2 fuses or 2 circuit breakers, for the most part, if you make the feeder half of the main, no more than half of the main, you're almost coordinated. Take this. That's rule of thumb. So if I have a fuse, for the most part, I have a fuse, and this fuse is feeding a panel, and here's my fuse here, and my fuse is here, and my other fuse is here, right? For the most part, if this fuse is 400 amp, if none of these fuses is higher than half of the 400, what's half of 400? 200. There's a 200 amp, 100 amp, 150 amp. If these are, the highest one is half of the main, you're almost guaranteed full coordination. Which means the main is twice as the largest feeder. The main is twice as largest feeder. Now here's where you can get into issues. Again, rule of thumb. Here's where you can get into issues. Take this. What if I have a fuse here, and this fuse was 300 amp? Now 300 amp fit from a 400 amp, you might not be able to coordinate these babies. So here's a rule of thumb. If your main is, whatever your main is, your largest feeder, don't make it higher than half of the main. Your main is a 1000 amp. The largest feeder is no more than 500 amp. Your feeder, as your main is 4000 amp, the largest feeder out of the 4000 amp is no more than what? 2000 amp. Does that make sense? If you do it this way, guys, you're almost guaranteed fully coordination, especially with fuses and almost with circuit breakers. So that's what this ratio for coordination, it gives you, most of it is 2. Can you guys see 2, sometimes 2.5 here, but for the most, here's a 3. based on the type of the fuse that you're trying to coordinate. There's a couple of threes here. But for the most part, if you can continue with 2-to-1 ratio between the main and the feeder, you're almost guaranteed coordination without doing the study, without doing any study. Okay, so that's basically what I wanted to show. This table, guys, you can have these tables in the industry you have in your book. Every manufacturer give you the available short circuit for equipment. Let's say a three-phase, because we're a three-phase system. Can you guys see it will give you the impedance and the short circuit. So let's look at this. I have at the terminal of this 25 kVA transformer, the full load current is 105. That's piece of cake. Here's the impedance, and here's the short circuit. And oh, by the way, this is not rocket science. You know what they're doing here? They're taking, here's how you found this one. You take the 25K divided by 240. That's how you found this. And then you take this, then this one, you take 104 divided by, this is an impedance, divided by 0.0158. And that's how you get these values. They might multiply it by 0.92. So the manufacturer of the transformers, guys, give you, here's a 100 kVA transformer, and here's all the information, the short circuit. So the nice thing about this, guys, since we're doing three-phase, let's go to the three-phase, because this is three-phase 208. Let's just say we have a 500 kVA transformer. 500 kVA transformer. What's the voltage? Is this three-phase? Let's say 500 kVA transformer right here. Okay, so if you guys look at the 500 kVA transformer right here, the short circuit at the terminal of a 500 kVA transformer is 124 kVA. 124 kVA. Given by the manufacturer. Given by the manufacturer. They did the calculation for you. They did the full load current and so forth. So you might have to have some current limiting fuses and so forth. Okay, so that's basically what I wanted to show you. We got these, coordination, we got that one.
Is this an NEC table?
No. No. And the last one, guys, is this baby. Oops, this is the wire size. This is, how do we flip it? No, I don't want that one. How do you, doesn't allow me to flip it. I know it does, but it, anyway, why don't you guys look at the one in your book? Can you look at this one, please, in page 423? Page 423 gives you the available short circuit from a 500. This is only for one transformer, only for one voltage. That's the disadvantage. Imagine if you want to change the transformer, the voltage, you have to have another table. This one is for a 300 kVA transformer, three-phase, 2% impedance, and they're giving it to you for four voltages, 208, 240, 480, and 600. Okay, can you guys do me a favor? If you look at, it's a 300 kVA transformer, so if your transformer is 250, this table is worthless. Does that make sense? Okay, if you guys look at zero distance from the transformer, if I'm using a 3-aught, can you guys see if I'm using a 3-aught at zero distance? At zero distance, can you guys see the number is the same for all of them? It doesn't matter, right? It doesn't matter. At zero distance, the impedance doesn't matter. Okay, do me a favor. Can you go to 480 voltage, and let's say we're going to go carry the let's say 500 kcm, because I like 500 kcm. Can you guys go to 500 kcm, one set, 500 kcm, 480, and the distance is, let's say, 500 feet. The distance is 500 feet. Can you guys find the short circuit at 500 feet, 500 kcm?
7,880.
Anybody second? Anybody second that? So at 500 distance and 500 kcm, 7,880, right? So that's how you read these tables. Now, thanks God we have software, so you don't have, otherwise, you're going to have a table for every single transformer size. So thanks God we don't have these tables, and we can use the calculation for it, guys. Okay, so let me just quick, guys, take you through the rest of the PowerPoint presentation. Then I'll give you. I got the best out of the stuff. I don't want to. I just want to highlight a few things when we go to short circuit. Let's go. Okay, when you guys do short circuit, there is line to line to line or line to line. The worst scenario, always the worst scenario, is line to line to line. Phase A, phase B, phase C bolted together. That's called line to line to line. LL is phase A, phase B. So if I have phase A, phase B, phase C, is A, B, C, go tie them together, bolt them together. That's what you're looking at. If you have phase A and phase A and B, this is what you're looking at. The worst scenario is always LLL, line, line, line. Make sense? That's what we're going to be calculating based on that one. If you have line to neutral, Ashley, can you see how you can derate 87%? They're telling you most likely if you have line to line, it's 87% of line to line to line. Okay? Line to neutral or line to ground are the same. Usually go from 25 to 125. Usually it's in, so most of the engineers, guys, they assume the default is this one. You calculate based on line to line to line. You're almost, I would say 95% of the time you're good if you accommodate for line to line to line. For that will cover line to line or line to neutral or line to neutral or line to ground, all these scenarios that you can get. Arc fault. So arc fault is everybody knows what an arc fault is. Arc fault is low impedance fault, low impedance. So it's not high, it's I'm sorry, high impedance. High impedance, it doesn't trip the circuit breaker so fast. It's a high impedance fault. If I have a high impedance fault, so if you want to find the fault that can create from the three-phase, guys, here's the multiplier, 89 or 1.25. Who cares? If the three-phase is 60, let's say 65 kiloamp here, then this fault will be 0.89 times 65K, and if it's a 2.8, it will be 0.12 times 65K amp. I always tell the students, guys, can you guys see how low the arc fault goes on the 2.8 compared to the 480? See how low? That's where the higher the voltage, the more damage the arc fault, arc flash, arc blast. So these are the values that we do. The software that we have, NIC, has the ability to evaluate based on arc fault. We run arc fault analysis next quarter. Again, prepping you guys for next quarter. We're going to be running a fault analysis. If you remember these data, it will help you a little bit. Okay, this is the calculation. We did that one. Current limiting fuses. If you have a current limiting fuses, guys, as we said, they filter the value. So if you have a current limiting fuse like this baby here, current limiting fuse, and if I have, here's my fuse here, and the available short circuit coming here is 63.5 kiloamp. By the time it comes to this area here, it might knock it down to 42 kiloamps because it trips fast within a quarter of a cycle, and it chokes the current that's coming in. Does that make sense? 63, you get into a current limiting fuse, it knocks it down to 42, almost to 42. And we have the circuit to size it. Okay, calculation. Talked about coordination, graphics. Okay, this one, selective coordination. Okay. Low level, and all these guys, I promise you, you're gonna hear a lot about these as we move into the industrial project. We do a lot of things about the coordination. Okay, the last thing I want to say, the contribution, guys, from the contribution from a three-phase from motors. If you have motors in your system, they always contribute equivalent to the locked rotor current. Okay, so take this. Very simple. and I'm going to write this one, and then I'm going to stop. If the available short circuit right here coming in is 33 kiloamp, and I have a big air handling unit right here, and this air handling unit is, let's just say for the ease of installation, let's just say it was 100 amp. 100 amp. It's 100 amp. It's in a horsepower, but it's 100 amp, just for the ease of installation. If they have a short circuit right in here, guys, you know what happened? If I have a short circuit right in the panel, that air handling unit start pumping current into the circuit. So it will contribute equivalent to its start current. The start current usually 5 to 6, let's just say 6. So that will be 600 amp. So the total short circuit right here is, it'll become 33.6 kiloamp. Can you guys see it? This is coming from Excel, from the transformer, and this is coming back from the motors. So long story short, if you have motors, air handling unit, chillers, rooftop units, all these pumps, when you have a short circuit, momentarily they change into a generator and they start pumping more current into the short circuit. So yes, your highest is 33 kiloamp, but if you have more motors, this is contradict what I told you before. I said the one closer to the transformer is always higher, right? Unless you have a lot of motors. If you have a lot of motors, you could end up here with higher than here, like we did, 33 coming from the transformer, but inside the switchgear is 33.6. Because your equipment or generator, have generator even worse if you have a generator. Your equipment motors will act as generators upon the existence of a short circuit condition, pump more current into the system. Just remember this as we move on. Okay, that's all what I want you guys to do. The formulas for calculating by hand, they're all in the book. I usually don't, I'm planning to do some of them next quarter when we do the calculation, the short circuit, do a couple of them by hand. But at least this is a good introduction for what's coming. Okay, shall we have 5 minutes? And I have one more thing for you, and then I'll let you go.